Hello everyone, I'm Yuki Tanaka from NEC. Today, I would like to talk about appearance-based curriculum for semi-supervised learning with multi-angle unlabeled data. In this paper, we consider a scenario where labeled training images from limited angles and unlabeled ones from various angles are available for training. For example, consider product recognition. One can obtain labeled images from a digital catalog, typically one or two per product taken from the front. On the other hand, unlabeled images can usually be collected in shops or stores using security cameras from unconstrained viewpoint. If such data can be used to train a product recognition model, annotation costs are greatly reduced. As a method for learning from labeled and unlabeled data, semi-supervised learning has been studied. A recent approach to semi-supervised learning, represented by fixed match, combines pseudo-labeling strategies and data augmentation. This approach implicitly assumes that most of unlabeled data can be covered by data augmentation. This assumption is helpful to study semi-supervised learning. However, it is too idealized for our scenario. This is because the labeled data is so sparse that data augmentation cannot cover the distribution. Indeed, our scenario is hard for conventional algorithms because widely available data augmentation cannot transform a photo taken from the front into a photo taken from the back. So we need to develop a novel approach that does not rely on this assumption. To tackle this problem, we propose appearance-based curriculum, ABC learning. The key point of this method is feeding into training from unlabeled images that are similar to labeled images. By taking our strategy, pseudo-labels for unlabeled images can be assigned with high accuracy. Our framework consists of a ranking phase and a training phase. The ranking phase determines the order of unlabeled data used in training. The basic idea is to use for training from unlabeled images that are similar in appearance to the labeled image. To measure the appearance similarity, we propose three criteria. The first one is angle-based similarity, which is the similarity of viewpoints under the hypothesis that two images of an object from similar viewpoints are similar. The second one is the local descriptor-based similarity, which is the similarity of off-the-shelf handcrafted local descriptors like Okatani, under the hypothesis that they are good at finding images of an object taken from similar angles. The third one is global feature-based similarity, which is the similarity of global image features. If you are interested in the precise definition and the formula, please refer to the paper. In the training phase, we execute semi-supervised learning following the order set by the ranking phase. Another important factor in ABC is when to feed the next unlabeled data set in training. In this paper, we employ the feed-on-plateau criterion, which feeds the next unlabeled data set when the proportion of pseudo-labeled images in an unlabeled set has stayed within a preset width for a patient period. To evaluate the effectiveness of our proposed method, we experiment with three datasets. The first dataset is Miro. Miro is a public dataset of 120 object images from various viewpoints by this figure. We treat this dataset as a 120 class object classification task, and in the training images, one image per object taken from a specific shooting angle was selected as labeled, and the remaining were used as unlabeled. This is the result of Miro dataset. Each column shows the result with labeled images taken from the given angle. We compare the accuracy of our proposed method with supervised learning and semi-supervised learning, including fixed match. Although our proposed method can be applied to any semi-supervised running method, in this paper, we use fixed match to apply our ABC method because fixed match is one of the state-of-the-art semi-supervised method, and yet it's simple. To see this result, conventional semi-supervised method, including fixed match, struggled with this dataset and even failed to be supervised, depending on the camera angle of a labeled image. On the other hand, our proposed method ABC outperformed all the baseline methods by a large margin. This indicates that the proposed method is effective in our scenario. This is analysis of pseudo-labeling during training in mirrored experiments. The red marks represent the accuracy of pseudo-labels. The blue marks represent the proportion of pseudo-labeled images in the set of unlabeled data. You can see the number of pseudo-labels in ABC grows much slower than that in fixed match. And also, the accuracy of pseudo-labels stays higher in ABC than in fixed match. This indicates that by controlling the order and speed of feeding unlabeled data, ABC generates cleaner pseudo-labeled data and leads to higher test accuracy as a result. This is also the result of other datasets, drink dataset and coil dataset. Drink dataset is a privately collected beverage product dataset, and coil dataset is a public dataset of commodity images. In both datasets, one image per object taken from the phone was selected as labeled, and the remaining were used as unlabeled. In drink dataset, ABC outperformed all the other methods, and in coil dataset, our method achieved almost the same accuracy as fixed match. This indicates that our method ABC was effective on the other dataset. To conclude my presentation, we consider a scenario where labeled images taken from limited angles and unlabeled ones taken from various angles are available for training. In this scenario, we propose an appearance-based curriculum, ABC method, that incrementally expands the pools of unlabeled images fed to a base semi-supervised running so that newly added data are the ones most similar to those already in the pool. In the experiment, our proposed method outperforms the state-of-the-art semi-supervised running method. Thank you for your kind attention.